So we have one last topic to talk about, and that is predicate logic, which is different from propositional logic. As I'm sure you remember, a proposition is a statement that's either true or false. So Kermit the Frog is green, 2 plus 2 is 4, 8 is prime, etc. And we can also abbreviate these and make woofs, which is what we've been doing so far this semester, right? So we can abbreviate these propositions as letters, like A is Kermit the Frog is green, B is 2 plus 2 equals 4, again, either true or false. C is the proposition, 8 is prime, and we can form some well-formed formulas, some woofs, by combining these things. So you can think of a proposition sort of like a Boolean variable. It's always true or false, right? Whereas a predicate is more like a method that returns true or false. So if A means Kermit the Frog is green, we might let G of X mean X is green. So, it's a method by itself. It doesn't have a truth value, but we can use a predicate to create a proposition. So we can say, look, if K equals Kermit the Frog, then G of K, the method that takes K sort of as a parameter, is a proposition that means Kermit the Frog is green. So remember, our propositions are things that are true or false, right? And our predicates are more like a method that returns true or false. So we might say f of xy means x plus y equals 4, but we still need to pick what are our parameters that we're putting in there. Let p of x means x is prime, b of x means x has a banner ID, and so on. And so we can come up with some constants, for example, and say if I is equal to 3 and j is equal to 6 and k is equal to Kermit the Frog, then we can write, all right, let's see. Kermit the Frog is green, and it's also the case that Kermit the Frog does not have a banner ID, and it's also the case that 3 is prime, and it's also the case that 6 is not prime, and it's also the case that, what was F? Oh yeah, so 3 plus 6 does not equal 4. All right, so this is sort of a woof, a well-formed formula, but it's made up of predicates with constants as parameters or arguments to the predicate. So we've got 3 things we need to think about. We have the predicate, which we just think about as though it's a method. It's a method that returns a Boolean. We have a variable, which is a parameter of the predicate that can take on lots of different values, right? So if we have g of x, x could be Kermit, x could be the moon, x could be a pencil, right? And then we also have some things that are constants. So they are specific instances of things in the world, like Kermit the Frog, or the number 42, or my pink baseball. And so we can take these constants and run them through as a parameter to our predicate to end up with a proposition. Now, just like when you're writing a method in Java, you can specify what is the type of your parameters of your argument. We kind of do that in predicate logic by talking about what is our domain. So for example, if our domain is limited to Rowan students and we have a predicate b of x that means x has a banner ID, then every single x that we put in here is only going to be of type Rowan student, and so b of x is always going to return true. Here's another example. On the other hand, if I change my domain and I say my domain is now American citizens, and I have the same predicate, b of x means x has a banner ID, but now I'm considering this predicate over the domain of all American citizens. Well, it's definitely not the case that all of the elements of our domain, all of the possible parameters that we can send to that function, have a banner ID, right? It's not the case that all American citizens, which are the things that could be set in as a parameter, have a banner ID. But we like to make statements about things even if it's not for absolutely everything in our domain. So we might make another statement that says, okay, if my domain is American citizens and b of x means x has a banner ID, well, we've said not everybody has a banner ID. But I could say there's at least one thing in our domain that has a banner ID. In other words, there's at least some American citizen who has a banner ID, right? So it's not all of them, but if I sort of ran this method on every single thing in my domain, sometimes it would come out true. Now, we often talk about, in predicate logic, we often think about the sort of everything in our domain and the at least one in our domain. So even if I switch my domain back to Rowan students, I can still say, if my predicate still means X has a banner ID, I can still say there is at least one X in our domain that has a banner ID. Yeah, my domain is Rowan students, and yeah, in fact, every single element of my domain has a banner ID. If I run B of X on anything in my domain, it's going to return true, right? But that doesn't matter if I'm trying to say there exists at least one. That's true too, right? All of them have banner IDs, but that also means there's at least one of them. So now we get into some fancy notation. We call this the universal quantifier, this upside down A, and it's really just a lazy shortcut for all. So if my domain is Rowan students, right, I can write, and sorry, B of X means X has a banner ID, just like it said this whole time. I can say for all X, B of X, right? And this expression here means all Rowan students have banner IDs, right? Because no matter what X you pick in your domain, for all of them, this is going to return true. On the other hand, if my domain is American citizens, it is not the case that for all X, B of X, right? It's not the case that everything in my domain is going to return true. So I stuck that not outside of there. And the other quantifier that we talk about is this backwards E, which stands for there exists, okay? And it's just a fancy way of saying there exists at least one, okay? There's at least one of these things. So if B of X means X has a banner ID, if my domain is Rowan students, I can say there exists at least one Rowan student, one thing in my domain that has a banner ID. And of course, I can say exactly the same expression for American citizens. There exists at least one X in my domain of American citizens that has a banner ID. And so really what I want you to learn to do here is to translate sentences into predicate logic. And the next step would be doing proofs in predicate logic, but we're not going to do that this semester. But I just want you to get a feel for, oh yeah, I can express this English sentence using predicate logic. So that's really all I need you to do. So for example, if I want you to say, if my domain is people and the domain is really important, and H is the is human predicate, and I want to say everyone is human, then I can write, for all X, H of X, right? Everyone in my domain is human. Every item in my domain, every element of my domain, all of them, if you run them through the is human thing, it will return true. Let's stick with our domain of people, and let's let B be the has brown hair predicate, right? Now, it's not the truth that everyone in our domain has brown hair, right? Our domain is people. There's people who don't have brown hair. But there is at least one person in our domain of people who has brown hair. So we're going to use that there exists predicate, right? This backwards E. There exists, and we need to come up with a variable. Maybe I'll use Q as my variable I'm going to use here. And I can say B of Q, right? Which says there exists at least one thing Q in my domain of people such that this B of Q predicate returns true, or the B predicate when run on Q returns true. And if you go look at the slides on Canvas, you'll see that I've put the answers for all of these in here. And mostly I tend to use X's and Y's just because that's what I default to. But when you are talking about one of these variables that you're putting in here, you can use X, you can use Y, you can use Q, you can use whatever you want. Just don't overlap the letters that you're using for the predicates. Now, we can also, in our domain of people, with our brown hair predicate, say that more than one person has brown hair. And now this gets a little bit trickier, because what I have to do, if I say there exists an X and there exists a Y, right? So these are two things in my domain, and I could say brown hair of X, right? And brown hair of Y. The catch is I also have to say in here, and X does not equal Y. Because if I don't say that, it's possible that this expression would say, oh, well, I'll just pick the same one thing for X and Y. So you have to say X isn't equal to Y if you're going to do this. And I've added this little note here, which says that, strictly speaking, we should have a is equal to predicate, right? So really what I should do is I should say something like, instead I should say, let E of X, comma, Y mean E equals Y, right? And then instead of putting in this X does not equal Y, I could say, and let's see, it's not the case that equal X, Y, right? And so that's sort of the fancy official way to do this, but it's so much easier to just allow us to use does not equal and equal, right? The not equal to and the equal to notation, that I'm going to just let you go with that. Okay. Again, it's always important to check your domain. My domain is people, and I want to talk about if G is the green hair predicate, and I want to say no one has green hair. Well, you know, when you think about that, there's two ways to think about it, right? One way you could think about writing it, and both ways are equally good. One way you could think about writing it is for all, I don't know, I'm going to go with X again just because that's what people usually do. For all X in my domain, everything in my domain, no matter what value of X I give it, it doesn't have green hair, right? That's one way to do it. Another way to think about it is there doesn't exist anything in my domain that has green hair. So in that case, I would say there doesn't exist even one, oh, maybe I'll use a different letter here, S, such that green of S, right? I could have used X there, I could have used Z there, I could have used Y there, whatever, but I just decided to use S to be different, right? And one thing that is kind of cool is there are, of course, multiple ways to express things, just like in predicate logic, just like there are in propositional logic. But if you remember De Morgan's law, where you were sort of pushing a not symbol in and flipping the and to the or, that sort of works in predicate logic. If you have a not symbol on the outside of something, you can push it through the there exists and put it here, and the there exists flips to a for all. Or if I want to push this not out, I can push this not out, so the not goes out, but the for all turns into an exist. So that's something you can just, that's sort of a trick you can do wherever you want. If you're wondering whether two things are two predicate logic statements are the same. So suppose that P of XY is the X is the parent of Y predicate, right? So order matters in here. The first one is the parent of the second one. And again, make sure you look at the domain, because my domain is people. Okay, and this says everyone has a parent. So what is this saying? This is saying that if you take a person, they always have a parent, and X is going to be the parent and Y is the person. So what do I want to say? I want to say for everybody in my domain, so that would be a for all, and I'm going to make it, I don't know, picking a different letter, W, just so you don't get too stressed out over letters. So for all of the things in my domain, there's at least one thing in my domain that is the parent of the W, right? So I have to say for all of the W's in my domain, there exists, I don't know, a Q in my domain such that Q is the parent of W. And so I'm just looking and I want X is the parent of Y. So the parent comes first. So I have to say P of, sorry, QW, which says Q is the parent of W. Q is the parent of W, X parent of Y. Yeah, that looks good, right? So every W, for every W in my domain of people, there exists a Q such that Q is the parent of W. All right, let's look at this one. It still says my domain is people. So the only things that are going to be parameters to my predicate are people. So how do we say that not everyone is a parent, right? Well, not everyone means either we could do, actually there's two ways we could do it, and it's back to that sort of De Morgan's law thing. We could say it's not the case that for all, we'll make them A's and B's this time, for all A's, there's somebody who A is the parent of. So it's not the case that for all A's, there exists a B such that parent A, comma, B. But actually, we can also do that thing where I said, let's push this not through, right? So, and flip the A to the exists, right? So, and see what does that turn out to say? So if I take this not and push it through, that becomes a there exists. So now we're saying there exists an A for which there does not exist a B such that parent A, comma, B, right? So what does this say? This says that there is some A, somebody in my domain, for whom there is no B that they are the parent of, right? But in fact, we can also push that not in through again and say, okay, well then if we push that not in through, we still have the exists and A, but we're going to push that not through. So now we've got for all B, and here's the not pushed through, parent A, B, right? So let's just look at this expression and see, what does this say? This says, there is something in my domain that we'll call A, right? There's some person in my domain. Remember, my domain is just people. So there's some person, we'll call them A, such that for every single person in existence, A is not the parent of B. So all three of these are completely legitimate and equivalent ways to write not everyone is a parent. Okay, our domain is people again, so we are only considering things that are people, and we want to say more than one person is a parent, right? So I want to say there exists at least two people who are parents, right? So now we got to go back to the X and the Y, and the X doesn't equal Y, or maybe not X and Y, maybe A and B, or maybe C and D, or maybe Q and R. So let's just think about this for a second before we try to write the whole thing out. I'm going to say I want to have two people who are parents. So maybe I'll call X the first parent and Y the second parent, all right? And I'm going to have to make sure that X doesn't equal Y. But my definition of parent, down here, I need to define what the children are. So this is going to be like parent 1 is my X and parent 2 is my Y. But they may not have the same children. That doesn't say anything about this. So I'm going to have child 1, maybe I'll call child 1A, and child 2, maybe I will call them B. So now what I'm trying to say is there is in my domain 4 people, right? Or so let's see. So there exists an X, and there exists a Y, and there exists an A, and there exists a B. And what did I say? I said that X is the parent of A, and X is the parent of A, and Y is the parent of B, And what else do we know? It says more than one person is a parent, right? More than one person is a parent. So we have to say that the X and the Y are not equal so that we get more than one person, though, I mean, maybe they're both parents of the same kid, who knows? That, it doesn't say anything about whether people are parents of different kids or whatever, so the A and B don't have to be different, but the X and Y do. So I'm going to say, and X does not equal Y. So that's the whole thing, and I'm going to put parentheses around that whole thing. I don't actually need them, but it just helps me to sort of look at it and think about it. Okay, so our domain is still people, and it says no one is, X is parent of Y predicate still, so no one is their own parent. No one is their own parent. So there's a couple of ways I could say this, right? I could say everybody in my domain, and I'm going to pick a different letter instead of X just because I want to show you I can do anything. So maybe I will do, what haven't I done yet? I don't know. E. For all E, right? I just need to make sure that I'm not using any of the predicate variables that I said I was going to use, like P here. So for all E, it's not the case that E is their own parent. Okay. But again, I can also write this slightly differently. I can think of this as saying there isn't anyone who is their own parent, right? So I could also write this as there does not exist a person, E, who is their own parent, right? And again, if you look, we've got that trick I showed you with the sort of De Morgan's Law type trick where there was the not in here. When I pushed it to the outside of the there exists, or when I pushed it to the outside of the for all switched to a there exists. But both of these statements are equivalent, and they both mean there isn't anybody in my domain of people who is their own parent. All right, next one, domain is still people. P of X, Y is still X is parent of Y. There's no person who is everyone's parent. So I'm just going to start thinking about this. There does not exist a person. So for there does not exist a person, I'm going to go back to using X, why not? There does not exist a person X such that for all Y, X is Y's parent, right? There does not exist a person such that no matter what you pick in your domain, that person is the person's parent, right? There's no person who's everyone's parent. And again, if you want to see that little De Morgan's trick to see what other equivalent expressions we could come up with, we can say, all right, well, if I push that not inside, it would become for all X, it's not the case that for all Y, parent X. Oops, that shouldn't have a, where's my eraser? Parent X comma Y, right? For no matter who you pick, it's not the case, no matter who you pick in my domain, every single person in my domain, it's not the case that they are everybody's parent. And lastly, we can push this not through again and see that it still sort of makes sense, makes sense that we have the same meaning even though we do that little De Morgan's trick. So if I have for all X, I'm pushing the not in, so I'm going to do there exists a Y such that not P X Y, right? So my statement was there's no one person who's everybody's parent. And the way it reads here is no matter who you pick, there is somebody who X is not the parent of. So they're all actually equivalent. Whichever one feels more natural to you as a translation is the one you can do. The big skill you're trying to get here is just how do I take an English sentence, right, and turn it into one of these predicate logic statements. So far we've only been talking about domains that are very specific, like we're only talking about people. But what if I say I have no specific domain? So now my domain includes people, it includes birds, it includes pencils, it includes tables, it includes headphones, it includes rowboats, it includes everything, okay? And I have the predicate B of X means X is a bird, and F of X means X can fly. Well, if I wanted to say, if my domain were birds, right? So let's just do this. I'm going to move over to the side for a minute so we can look at this and then we'll come back. If my domain were birds, and I was trying to say not all birds can fly, and remember please that my f of x is x can fly. If my domain were birds and I wanted to say not all birds can fly, then I could just write there exists an x such that x can't fly, right? Because my domain is birds. So everything in my domain is birds, and I just say, oh, there's something in my domain of birds that can't fly. But we're not using the domain just of birds anymore. This slide says no specified domain. So our domain contains everything. So what I want to say, if I want to say not all birds can fly, then I have to say there's something that is a bird and it can't fly, right? Because I'm not talking about pencils. I'm not talking about tables. I just want to talk about birds, and I want to be very specific that I'm talking about birds. So what I have to say is there is something X, and it's both the case that X is a bird because my domain has everything, and it's the case that X cannot fly. Now we're back to that more than one trick, right? If I want to say more than one bird can't fly, and I'm still in no specified domain, so I have to sort of make sure I make it clear that the thing that I'm looking at is in fact a bird. So what do I have to say? There's more than one bird that can't fly. So there's two birds. Let's call my birds A and B, I guess. And what I want to do is I want to say, oh, I can't call them B because B is my X is a bird. So let's call my birds X and Y. So I'm going to say there exists an X, that's my first bird, and there exists a Y, that's my second bird. And what do I need to tell you about them? The first thing I need to tell you is that X doesn't equal Y, right? They're different. And it's also the case that X is a bird, and it's the case that Y is a bird. Let me shrink this a little bit. And it's the case that X can't fly, so not fly X. And it's the case that Y can't fly. So that's one big statement. And we need to put parentheses around all of that. Oops, sorry, my pen's not working. And it's worth noting that last time I did this, I did the order of these things differently, but they're all ands, so it doesn't really matter, right, what order I did them in. Here I said there's an X and a Y, X is a bird, Y is a bird, X and Y are not the same, and X can't fly and Y can't fly. And I will fix this on the slides, but you can kind of see here, maybe it's obvious that I manually put in these parentheses. It's important for the way the rules of precedence work with these exist things that if you have something that's bigger than just one statement, you have to make sure you put parentheses around them. So you'll see that in some of these expressions that I do, and I'll explain it in a little bit. All right, so we're going to stay in the no specified domain. Our domain contains everything from people to ducks to birds to pencils to rowboats. And I'm going to give you some predicates, and we're also going to add a couple of constants in here because we're going to use these predicates and constants for a few examples here. So if I want to say all days are sunny, how do I say that? What I don't want to say, and maybe I'll do this in red so you can see that it's wrong, or you'll get an idea that maybe it's wrong. Oops. So I can't say for all x, s of x, because that says everything is in my domain is sunny, right? It says that pencils are sunny and flowers are sunny and cars are sunny, right? And we can't say that because I have no specified domain. My domain has everything. So let's cross that out and let's talk about how we say all days are sunny. Okay, so what we need to do if we want to say all days are sunny, is we want to say everything that is a day is also sunny. So first you have to make sure it's a day, and then if it's a day, then it's sunny. So what I'm going to do is I'm going to say for all x, right? If x is a day, then x is sunny. So how do I say if then? Well, if x is a day, that implies x is sunny, right? And it doesn't actually tell me about anything that's not a day. So, you know, maybe people have sunny dispositions and we could talk about that. But this is how I express. If I don't have a domain specified, then I have to start with if it's a domain, then it's sun. If it's a day, then it's sunny, because I'm talking about everything here, right? And in fact, before I forget, it's super important, since we have more than one thing after the for all x, that we put parentheses around that. All right, let's talk about this one. I want to somehow express that there exists at least one day that's not rainy, okay? And so, and notice that in this example, sunny and rainy, it could be both sunny and rainy on the same day, given that I have these predicates. So at least one day is not rainy. So there exists something, and what do we know about that thing? That thing is a day, and it's also not rainy. So I'm going to write it like this. There exists an x such that x is a day, and x is not rainy. And let's put some parentheses around that. Now, the question is, when do you have to use implies, and when do you have to use the, the arrow for implies, and when are you using and in these things when I'm doing the no specified domain? And I guess the answer is, if you're talking about everything, then you need to make sure you say for everything, if it's a day, then blah, blah, blah. Whereas if I'm just saying there's one thing that is both a day and not rainy, then I do that. So it's a sort of a difference between the exists and for all in terms of the language that you're being asked to translate. All right, let's look at this one. Again, remember, no specified domain. So every day that is not sunny is not rainy. And we might want to think about translating that, since we have no specified domain. We may want to try and translate that into a little bit more clear English, right? So this says, if you've got something in your domain, so if you have something in the domain that is both a day and is not sunny, that means it'll be it's not rainy either. That means it's not rainy either. Okay? So if you have something in the domain that's both a day and it's also not sunny, then it's not rainy either. So what we need to do for this is, and this was a for all, right? Every day that's not sunny is not rainy. So let's take a look. So I have to say for all things, I'm going to call it X again, I'm getting boring. If X is a day and it's not sunny and not sunny of X, you have to have these things true before you can say it's not rainy, right? So everything that is both a day and not sunny, if it's that, then it's not rainy. And again, I need parentheses around that whole thing. Can't quite see them in here. So I'm sort of using the not again here, right? The implies again here. And again, I'm talking about for everything. There's a good chance that if you have no specified domain and you're starting to talk about an everything, that you may have to start out by saying, well, if I'm talking about all days and there's no specified domain, I better make sure it's a day. And if I'm talking about all non-sunny days, I better make sure it's a non-sunny thing and it's a day. And then I can have a then, therefore, with my implies. Okay, so let's do this one. Some days, and I said more than one, are both sunny and rainy. So we're in the there exists territory, right? Some days, but it's got to be more than one. So maybe we're going to talk about day X and day Y. And we definitely have to have the X does not equal Y. So let's see. There exists an X and there exists a Y. And what do we need to know about? They're both days. So day of X and day of Y. And we better mention that they're not equal because we said at least two. And they are both sunny and rainy. So that says that, and I'm going to wrap around here. I'm sorry. But so it's a day, X is a day, Y is a day. X doesn't equal Y. And X is sunny. And Y is sunny. Oops. And X is also rainy. Oops, sorry. And rainy X and rainy Y. So it's getting big, but again, I'm talking about some, so it's all of these things are true for X and Y. There is some, at least two, there's at least two things in my domain that are different because I said X doesn't equal Y, so they're different. They're both days, they're both sunny, and they're also both rainy. Okay, again, no specified domain. No days are sunny and rainy. So we can do a no as there doesn't exist, or for all it's not the case. So let's just try and do both. And again, since we've got the no specified domain now, we have to be a little bit careful with what are we doing with the implies or whatever. So if we start with the there doesn't exist a thing, so I guess I have to say I'm gonna say no thing that is a day is also sunny and also rainy, right? No thing that is a day is also sunny and also rainy. So if I want to do that, then I'm just going to use my there does not exist a thing X. And now we're just going to use ands, right? So there's no thing, there's nothing that exists, there's no thing that is day and also sunny and also rainy. Okay. So this is sort of, right? Remember the parentheses are going around this whole thing. There does not exist next this thing. If we want to talk about it in terms of for all X, then we can say, oh, all right, well, for all X, if X is a day, then it's not sunny and rainy, right? So if we look at our sentence again, our sentence is no days are sunny and rainy. So for all X, if it's a day, then it's not sunny and rainy, right? So we could say for all x, if it's a day, again, we got the for all, so we sort of have to, and the no specified domain, so we have to do the d of x, implies it is not sunny x and rainy x. And again, we need to put sort of parentheses or brackets around the whole thing. Oops, and I never matched that sunny one with two braces, right? So this guy needs to have a matching parentheses too. And for those of you who want to try, I'm not going to take time on this right now, but what you can do is you can see that if you push this not inside, it turns the for all x into a not, right? And so that becomes not this thing. And if you use some of your logic equivalences that you learned, you'll learn that if we put the not on this whole thing and we use De Morgan's, you can turn it into this equivalent. Now, sometimes you want to talk about specific things, like remember our Kermit the Frog is green? So I might want to say it rained both Monday and Tuesday. That's really easy. I just use my predicate and my constant. So it rained on Monday and it rained on Tuesday. And I don't need to do anything with the for all and there exists because I'm just using some constants. Now, the thing is that, you know, we've been saying, oh, R of X means it's raining or whatever. But you don't actually need to know what everything means in order to mess with predicates, right? So suppose that X, Y, and Z are variables, A, B, and C are constants, and P, Q, and R are my predicate letters, okay? And I tell you P of A and P of B and P of C. So these are all constants, right? If I tell you that X's domain, that my whole domain is A, B, and C. So X could be A, or X could be B, or X could be C, right? And that's all X can be, right, in my domain. Then what can I conclude? Well, I can conclude that well, since I don't know that my domain is just A, B, and C, don't know what A, B, and C are, but that's my whole domain, and I also know that whatever this predicate P is, it's true for A, B, and C, then I know that no matter what X I pick in my domain, P of X is true. And I also know that there's at least one X in my domain where P of X is true, right? In fact, it's all the X's in my domain, but I can say both of these things. So let's just take this sort of theoretical experiment a little bit further. Suppose I know that the P predicate is true for A, B, and C. But now the X, my sort of domain, is going to be not just A, B, and C, but also D, E, and F. And the question is, what can I say about X? And what can I tell you? Well, I can tell you that there's at least one X such that P of X. In fact, if my domain is A through F, I know that at least one of these things exists in here, right? In fact, I could say there's at least two or at least three because I know it's true for three things. What I can't conclude is that all of these are, you know, P of X or aren't P of X, right? I can't say, let's do it in red again, so it's sort of bad. I cannot say for all X, P of X, right? Because I don't know if it's true that P of D, E, and F, right? I don't know if P of D is true. I don't know P of E is true because I didn't tell you, right? So I don't know that for all X, P of X. I also don't know that it's not the case that for all X, P of X, right? Because maybe it is true that P of D is true and P of E is true and P of F is true. So then that would be true. I just don't know. So I cannot say these things because I just don't know. All right. But what I can say is there's at least one, I could even say there's at least two or at least three things that are in my domain for which P of X. So here's another tricky one. Suppose that I have ors in here instead of ands, right? And my domain, I've shrunk it back. My domain is just A or B or C. Well, sorry, my domain includes A and B and C, and that's it. Anything I'm only, just like we only looked at people, or we looked at everything in the world, no specified domain, I'm specifying my domain. My domain is just A, B, and C, whatever that is. Okay? What can I conclude from this? Well, since this was an or, I know at least one of them is true, but I don't necessarily know which one, so I could say there exists an X, P of X. Certainly can't say for all of them because I don't know. It might be true for all of them, but I don't know. All right, I've messed with the parentheses on this one. Notice that this this piece is parenthesized. So now I'm telling you that P of A or both of these or all three, right? So I know that maybe P of A is true or maybe both B and C are true. It's also possible all three of them are true. What can I conclude? Well, all I can conclude is there's at least one for which it's true. I don't know if it's true for all of them, but there's at least one. All right, check this out. It's getting a little bit weird. What I have done is B in here, right, is a constant, right? I said B was a constant. And my domain is still just A, B, and C. So those are the only things in my domain. But I've said it's true that, I don't know what P is. Maybe it's greater than or equal to. So I know A is greater than or equal to B is greater than or equal to B, and C is greater than or equal to B. Or maybe it means is the parent of. Who knows, right? All I know is P has this relationship with A and B, and B and B, and C and B. So what can I conclude if my whole domain is just A, B, and C? Well, since every time I run P on a pair, right, it always P's B as the second element of the, that's always true for the second element of the pair. I can say for everything, no matter what X you pick, it's true that P of XB. And I can also say, well, there's at least one for which P of XP. Of course, we know it's all of them, but if you know it's all of them, that also means there's at least one of them. Just a quick heads up about the textbook. In class, I've been using any old letter to represent any old thing. So I've used B as a constant or a proposition or as a predicate. And the textbook, when you read it, I should say, wants to save space by saying things like, if you see A, B, or C, it's always going to be a constant. All right, fine. You just need to know that when you read the book. So here's the summary of book notation. They always use X, Y, and Z to be variables. They always use A, B, and C to be constants. They always use P, Q, and R to be predicates. And to be honest, it's a good practice. Nothing wrong with it. So you need to know the rules of precedence for propositional logic. And basically, what we do is if any of the quantifiers or negation symbol appear next to each other, then the rightmost symbol is grouped with the smallest woof to its right. So the rightmost for all, or there exists. And so that's why I was putting in all of those parentheses everywhere, because what happens is when you get to something yucky, like, let's look at this bottom one for a minute, right? This exist X hooks up with the thing that's just to the right of it, and so the parentheses end up weird like that, which we don't want. So, or in fact, also this one here, right? This looks like it's one big exist for that whole thing, but in fact, this exist X is only there's exist something for that part implies, and then I guess X and Y here. So here X is a variable, here X and Y are constants, I guess. It gets messy. What I'm going to say is please put lots of parentheses on your predicates, and yeah, just put lots of parentheses on them. So just like with parentheses, we can talk about the scope, and so the scope of the quantifier, right? In the absence of parentheses, the scope of the quantifier is the smallest woof immediately to its right. So same thing as the how you parenthesize it. It's talking about when you're talking about for all x, like all xw, you got to know when is x a variable for, and it's the variable for w. So in here, just like if I asked you how do you parenthesize this, and you'd have to say, oh, well, since there's no parentheses written here, I have to take this for all x, and it goes with the woof that's closest to it, so I guess that's how it gets parenthesized. So therefore, the scope of the for all x is just that part. Whereas if I parenthesize the whole thing, then its scope, where this x is saying everything, whenever you see an x in here, that thing is going over the whole thing. Similarly, since this for all x has this giant set of parentheses across that whole thing, its scope, when we talk about x, we're talking about every single thing in the domain, and that's true over all of this stuff. And if I'm trying to figure out what's the scope of the exist a y in this thing, well, here's the exist a y, and its scope is the one piece to its right. So it's just that piece, right? And the whole and r of x isn't in the scope of does not exist a y. So again, put parentheses in your woofs. So we're on to the last part. If I want to know how do I, what's the scope of the z in here? When we say for all z, which z do we, what variables do we mean? Well, it's from that open parentheses to that closed one. So it's just this piece. Oops, that's the closed one.